Applications are developed by following the disciplines and iterations of the unified process. Application development follows a methodology, develops models, and uses automated tools. Most application development cycles include two sets of models, requirements models and design models. Integrated suites of automated tools support the application development process. An IDE includes tools such as a program editor, screen and report designers, an intelligent compiler and link editor, a symbolic debugger, and extensive documentation. Case Tools provides a tool suite to support a wider range of development tasks. A front-end case tool supports developing requirements and design models. A back-end case tool generates program source code from models. Executable software consists entirely of CPU instructions. Programmers write programs in higher-level programming languages that are translated into CPU instructions. Programming languages have evolved through many generations, and the most recent types are object-oriented and scripting languages. Later generations have incorporated improvements in capabilities, such as instruction explosion, database access, support for GUIs, and non-procedural programming. All programming language generations other than 1GL must be translated into CPU instructions before execution. A compiler translates an entire source code file, building a symbol table and an object code file as output. An interpreter translates, links, and executes source code programs one source code instruction at a time. Compiled and interpreted programs must be linked to libraries of executable functions or methods. A link editor statically links external reference calls in object code to library functions and combines them into a single file containing executable code. It also produces a memory map showing the organization of all software modules, which is useful for debugging. A link editor can also dynamically link external calls by statically linking them to an OS service routine that loads and executes DLL functions at runtime. Interpreters always use dynamic linking. First-generation languages are the earliest programming languages. These required programmers to remember binary codes that represented each CPU instruction and to specify all operands as binary numbers. This is tedious to program, and it was very error-prone. Second-generation languages are commonly known as an assembly language. This uses mnemonics to represent variables, CPU instructions, and data items. A variable is program instruction memory address. Label, data item memory address. This is easier to manipulate than binary numbers. The assembler translates program into binary CPU instructions. These were commonly in the 1950s, but they are rarely used today. Third generation used mnemonics to represent instructions, variables, and labels. Translation is done with compilers, link editors, and interpreters. Third generation languages are machine independent and were developed before GUIs, database managers, and the Internet. Fourth generation languages. Common features include higher instruction explosion than 3GL, better support for graphical user interfaces or GUIs, better support for relational databases. Some enabled non-procedural programming, for example SQL, and the majority were proprietary. Many were optional components of a database management system. The fifth generation of languages are non-procedural language suitable for developing software that mimics human intelligence. Rule processor accepts a starting state as an input and iteratively applies rules to achieve a solution. They have first appeared in the 1960s but were not widely used until the 1980s. Java, object-oriented programming language in its program execution environment. It maximizes the reliability of applications and reusability of existing code. It has a standardized target machine language for Java interpreters and compilers. The drawback to Java is that reduced execution speed due to the use of interpreted bytecodes and OS translation. A compiler translates source code into source code instructions, library calls, checks for syntax and other errors, issues warning or error messages, updates internal tables that store information about data items and program components, and generates CPU instruction or library calls to carry out the source code instruction. A compiler uses different rules or methods to translate different statement types, data declarations, data operations, control structures, function, procedure, or subroutine calls. A link editor searches an object code file for external function calls. It finds matching functions in a compiler library, and if the link editor can't find executable code for an external function, it generates an error message, produce no executable file. The key benefits are a single executable program can be constructed from multiple object code files compiled at different times, and a single compiler can generate executable programs that run under multiple operating systems by using a different compiler library for each operating system. Symbolic debugging. It's the use of an automated tool for testing executable programs. It traces calls to specific source code statements or subroutines, traces changes to variable contents, executes source code instructions one at a time, and detects and reports runtime errors to the programmer. It uses a symbol table, memory map, and source code files to trace memory addresses to specific source code statements and variables. It inserts debugging checkpoints after each source code instruction, and program execution can be paused. Debugging versus production and distribution version. It's incorporated directly within most interpreters. We have explored the application environment. We have discussed the software development process, looking at the evolution of the programming languages. This included looking at the compilation and link editing process. We discussed the characteristics of the use of an interpreter along with debugging tools as the use of an IDE.